we just finished two examples for the bending stress calculation. So we go to the third example is determine the normal stress and shear stress. So now we need to calculate also the shear stress at point B for the cantilever beam of AC. The cross-sectional area of the beam is as shown below. So this is a simple rectangular shape beam. So this is the B is 80 and then the hash is 160. Okay, so the point B is located 35 mm here from the bottom. Okay, so to determine the normal stress at B, bending moment B should be calculated. So just now the example here, we need to know the bending moment and then the shear force. So we can use the cut section methods here, cut from the force, okay, before the support. So total MB, okay, total MB here, we can cut at the point B, cut at the point B. So total MB here will be MB equal to MB plus 35 times 2.5, because this is clockwise, so this is also positive. So MB equal to negative 87.5 kilonewton meter, and the V is equal to 35 kilonewton. Okay, total Fy equal to 0, and then this is total moment B equal to 0. Then you obtain this value. Okay, after that you can calculate Ixx and Yyy. So for normal rectangular shape, so BH power of 3 over 12, you get this value. B power of 3 hash, you get Iyy. So same thing, we choose the greatest value of Ixx. Okay, so after that, okay, we list it out. So you can see that the centroid here is X for 40 and Y for 80. Okay, and then the normal stress at B now we need to find here. So this is 35 for the B to the bottom. Okay, so just now previously I mentioned 35 to the centroid, but it's actually 35 to the bottom. Okay, so 80 minus 35, you will get the distance here from B to here is 45. So here to here is 45 mm. Okay, so MB equal to the bending moment at B. Okay, this one they want you to use the bending moment at B, so you can find the MB at here. Okay, you are not using the maximum moment, but you are using the actual moment happened at point B. Okay, so you're using this value times YB. YB is the value for 45 over Ixx. So you get this value. Okay, so here I also listed how you need to do it for the unit conversion, so you can practice also at home. So after we calculate the normal stress, now we can calculate the shear stress. For shear stress is a little bit different. Okay, so you can see that from Y here, you can either choose, as the formula I explained just now, you can either choose the area at bottom or area top above the top for the equation of VAY over IT. So the area now is 35 times 80. Okay, and then the Y1 is, the Y1 here you need to be careful, and then I already listed here, you can see that Y1 here is 80 minus 35 over 2, means this is the centroid of this area to the centroid of overall. So you need to remember the Y will be the centroid of the area to the centroid of overall. Okay, so you calculate the Y1, you will get 62.5. So you input into the formula, you get AY1. Okay, if you don't want to do like this, if you just want to directly put into the formula, there is no problem. So V, just now you calculate 35 kilonewtons. Okay, and then you input into this, and then I, you input the value of I, and then the T is the thickness of D, this one, 80. So you input all the value, you calculate, you will get the shear stress at B. Okay, so this is also another example to show you the same thing. Okay, you can use the area on top. So area on top will be 125 here times 80 times 17.5, because this area, the centroid here of this area, which is 80 times 62.5, then you will get 17.5. Okay, this is 80, this is 80. Okay, so 80 minus 62.5. Okay, so you will get the centroid of this. So you get the y value of this. So v times a times y over it. Okay, then you will get this value. You can see that both values are the same. So basically, how you calculate the shear stress is using the centroid of the area to the centroid of overall. Okay, so we can go to the last example here. Okay, so we can look at this. The steel beam with standard size of UB 254 times 102 times 28 kg per meter is subjected to maximum shear force 30 kilonewtons. Sketch the shear distribution along the cross section of the beam. So they want you to find the shear force for point A, B, C, D. Okay, so this is a symmetry beam, so we don't need to calculate the bottom part because you can mirror the answer for the top part to the bottom part. And then here the B and the C is different, is the thickness. For B we will use the thickness of flange, and for C we will use the thickness of web because it's located at the web. Okay, so solution is they already give you the value at the standard size. So from the table, okay, you can check the table for the steel. Okay, then you can I equal to 4008 cm power 4. Okay, and then centroid is 51.05 and 130.2. So on top, tau equal to 0 because of what? Tau equal to VAYB over IT. So the A will be 0, then the value of tau, the shear stress will be 0. Okay, because area we can choose either the top or bottom, right? So this will be 0. Okay, and then the bottom part, the bottom part, the tau B. Okay, tau B is the point for B. You can see that the value here, A times YB. So A here is 102.1 times 10 times the area of at the location of Y, which is 125.2. 125.2 I listed here. The YB is the centroid for this, which is 10 over 2 for this 5. Means it's the overall 130.2 minus the value of top. Then you will get this YB is the value of 125.2. Okay, so you input the value of V 30, A, Y, B. Then you get this value. And then times OA over I, either IXX value, and the I from the table, and then the T is the 102.1 because it's located at the flange, so we get the T of this. So we will get the value of 0.937 kilonewton and Newton per millimeter square. Okay, so for the unit conversion you can practice at home, or either you don't want you use it, then you can remain the kilonewton. Okay. So after that, we can calculate the point C. For point C here and here, it is the same because it is located at the same web. Okay. So for C here, we can calculate. What is the different things here is the AYC will be the same because it's located the same centroid for area number 1. For area number this one, the top part to the centroid of the overall. But then here now, everything is the same except the T. T is the thickness of the web. Okay, so we can input the value, then we can see that we will obtain the higher shear value. Means that even at the same YC location, if the point at the web is experiencing higher shear stress compared to at the flange. Okay, so after we calculate the tau C, then we calculate the shear stress at point D, which is located at the centroid. Okay, so here we can calculate is AYC. So here you can see that we can see that this plot we divide to two areas because we have AYC for the area number 1 and area number 2. Okay, because they have different dimensions, so we need to break it to two parts. So AYC equal to the same value as the previous, the video. Okay, so A times YC and A times YD. YD is the centroid of this area number 2, which is this D. Okay, 120.2 means is 130 minus 10. So you will get this is 120.2. Okay, to the centroid. Centroid is here is 0. Okay, so directly you will get 60.1. So you get the value of AYC and AYD. So you get the total AYC and AYD is this value. So the shear stress at T is V times AYD over IT. So you input value of the V and the AYD and then over the I times the thickness of web, because C is located at the web. So you will get the value of tau T. So after you obtain all A, B, C, D points, then you can calculate and then you can draw the shear distribution diagram. Okay, for the shear distribution diagram is you calculate you input the value of tau M, means starting is 0, and then through this point it will become 0.937, and then you will increase become tau C at the webs, the thickness here is 14.95, and then at the central it will be the highest value, which is 20.36, and then here you mirror the value. Here is also the value of tau C, tau B and tau A. So this is the diagram for I-beam. Okay, so this is symmetry, so you will get the same. If your I-beam is not symmetry, then you need to calculate every single point until bottom part, then you can plot it. So here I want to make a summary. So for T-beam, you will get the shape. Okay, this is the bending stress at top and bottom, which is uneven, it's not symmetry because you will experience different value. And then this is the shear stress distribution, the shearing stress. Okay, so for the flange and for the web, the value here, and then this is the maximum. Okay, so here is the I-beam. Just now I explained that. So this is the symmetry normal stress for that, and also this is the shearing stress for that. Okay, so the today calculation lessons is until here. So I hope you can practice at home. Okay, see you again. Bye bye.